Hello, welcome to the first lecture of heat transfer. What is heat transfer? When thermal energy is transferred from one point to another, it is called heat transfer. Suppose this is fire and this is the iron rod. We place the one side of iron rod on the fire. These are the atoms. These are the atom of the iron rod. When the fire reach to this side, the atom become heated. These heated atom transfer thermal energy to their neighbor atom. This neighbor atom transfer energy to this neighbor atom. This neighbor atom transfer energy to their neighbor atoms, and so on. So the heat transfer in this direction. After after some time, this side become heated, and the heat transfer in this process is known as conduction heat transfer. We will discuss conduction later. Conduction heat transfer will discuss later. So there are many methods. So this is the simple example of heat transfer, in which heat transfer from one point to another point, and heat is a thermal energy. As we know, there are many forms of energy. One is light energy, sound energy, mechanical energy, etc. So heat is a form of energy, and it transfer from one point to another, and this is known as heat transfer. There are mode of heat transfer. Mode or method of heat transfer. Heat is transferred from one point to another by three methods. One is conduction, one is convection, and the third one is radiation. Now what is conduction heat transfer? The transfer of heat from most energetic particle to the less energetic particle is known as conduction heat transfer. Suppose this is a cylindrical material. Suppose this is a material, we heat it from the base. These are the atom of which is from which this material is made of. This is the base of cylinder. When we heat the cylinder, the first of all these atom become heated, and these heated atom then transfer their energy to their neighbor and so on. So the heat transfer in this direction, and this is the conduction heat transfer. These are the less energetic particle, and these are the high energetic. These are the high energetic particle because it is present. It is near to the base, and heat transfer, first of all heat transfer to these particle, then transfer to their neighbor atom. So this is the conduction heat transfer. Now conduction heat transfer. Now which law is used for conduction heat transfer? So the law used to determine the heat transfer uh, by conduction is known as Fourier law. It is used for conduction heat transfer. Suppose this is a three-dimensional wall which is made of concrete or something else, but ignore it this time. We will discuss it in chapter number 2. For simplicity, this is the x direction, this is the y direction of the wall, and this is the z direction which is into the plane. But we discuss these in later. For simplicity, this is a wall which is made of concrete. This is the hot air which is at T1, and this is the cool air which is at T2. This is the thickness of the wall. When heat transfer, the heat transfer from high temperature region to lower temperature region. So the heat transfer in this direction, and transfer through the thickness. So now mathematically we determine the heat transfer through this thickness by Fourier law. Its mathematical form is Qx is equal to minus Ka dt by dx. So Qx is the heat transfer in x direction, K is the thermal conductivity of material, A is the cross-sectional area of heat transfer, dt by dx the temperature gradient or slope. So dt by dx is T2 minus T1 divided by x2 minus x1. Put equation number 2 in equation number 1. This is equation number 2. This is equation number 1. When we put equation number 2 in equation number 1, we obtained Qx is equal to minus Ka T2 minus T1 divided by x2 minus x1. Now this T2 is less than T1 because this was the wall, and this was T1, was T2, and the temperature T1 was higher from temperature T2. So T2 is less than T1. This is become negative, and x2 was higher from x1. So this negative multiplied by this negative become positive, and this this was obtained, the final equation was Qx is equal to Ka T2 minus T1 minus T2 divided by x2 minus x1, or simply Qx is equal to Ka dt by dxo. Now what is Qx? It is the heat transfer in x direction. Qx is the heat rate, which is heat per unit time, is the cross sectional area. Now what is the cross sectional area for heat transfer? It is the perpendicular area. Suppose this is the this is the cross sectional area, this is the heat transfer, which is Qx, and this is the area. This area is perpendicular to heat transfer. So dt by dx, so Qx, the unit of Qx is joule per second. The area of the unit of area is meter square. These are the SI units: dt by dx, T is temperature in Kelvin, and x is meter. So from one, so suppose if we obtain, so for thermal conductivity we rearrange this equation: dx into Qx divided by A divided by dt, which become thermal conductivity, and the final form K is equal to Qx dx divided by A into dt. The unit of Qx joule per second, this is meter, and this is the meter square, and this is the Kelvin. So for simplicity, the final form is joule per second 1 over meter 1 over Kelvin, and joule per second is watt per meter into Kelvin. The unit of thermal conductivity is watt per meter into Kelvin. The thermal conductivity is a function of x, y, z, and material. So sometimes the thermal conductivity for some material, that thermal conductivity changes with direction. Suppose so the thermal conductivity in some material changes in this direction. Thermal conductivity is value of thermal conductivity is 1, and the thermal conductivity in this direction is different. So these are sometimes different, and for some material these thermal conductivity are same. The material for which the thermal conductivity are same are isotropic material, and for the material for which these thermal conductivity are different are called anisotropic material. We will discuss thermal conductivity in detail in this chapter. And thermal conductivity for different materials, suppose for solid, liquid, and gas, these thermal conductivity are different. Now now what is the heat? The heat flux. Heat flux is the heat per unit area per unit time. The joule per second is the heat per unit time, and area is meter square. So watt per meter square is the unit of flux. The is Q is equal to Kx is equal to Ka dt by dxo. Now if you divide both side by A, both side divided by A, so this become Qx by A is equal to K dt by dxo. Qx by A become the heat flux in x direction, which is Qx by A is equal to K dt by dxo. Now suppose this is the cylindrical rod, and this is the cylindrical rod, and this area, this is the cross sectional area, which is A cross sectional area, and this is the heat transfer in x direction, and it transfer in per second. So Qx per unit area per second is flux, and this is the cross sectional area. This is also the cross sectional area, which is perpendicular to the heat Qxo. The heat, the Qx and the area become perpendicular 90 degree. So this is the cross sectional area. Sometime we use this area, which is the surface area for heat transfer. In heat exchanger, sometime in most of cases we use this area, because these areas sometimes we neglect and these become small. Suppose this is rod, these areas are very small as compared to the surface area, so we ignore this area, and this is the we use this area, which is the surface area. The for rod, the cross sectional area is pi r square, which is phi d square divided by 4, and the surface area is 2 phi r l. 2 r is equal to d, so pi dl is the surface area for the cylinder. So most of cases we use these surface area in heat exchanger, which we will discuss in chapter number 11. Thanks.